In 2.5, we have the goal to be able to take the derivative of functions that are implicitly defined. What does that mean? Well, we'll get there. First of all, let's do a quick review of the chain rule since we're using that a lot here. The derivative with respect to x of the sine of x. Nothing crazy here, just the cosine of x. The derivative with respect to x of the sine of something else, like chocolate. Well, remember, first we deal with the sine part. That's the outer, that's the shell, and its derivative is cosine of whatever's inside. Then we do the derivative of what's inside. If it's different than x, that means it's a composite function. So we take the derivative of the chocolate. Chocolate derivative. What is the derivative of the chocolate? What's the slope of chocolate? Something to ponder. Derivative with respect to x, really what I'm getting at is we have a different variable. We don't see an x there. So that's a chain rule. We first do the derivative of the outside, cosine, leave the inside the same. But because the inside is a different function, like u, now we have to take the derivative of that different function, of that u, with respect to x. So times du dx. Well, it doesn't matter if I call it chocolate, if I call it u. If it's something else besides x, I have to multiply by that something's derivative. Like in this one, the derivative with respect to x of the sine of y. So I have to first do the derivative of the outside, cosine, without touching the inside, then say, what's the derivative of the inside? Dy dx, the derivative of y with respect to x. We are going to have to deal with this kind of chain rule all throughout implicit differentiation. What does implicitly defined functions mean? If a function is implicitly defined, that means we can't solve for y. So it's for when I can't solve for y first. I can't solve for y first. So look at a bunch of these examples down below. Can I get y by itself in this equation? No. Can I get y by itself in this equation? No. Maybe I can get y by itself, but uh-oh, there's another y. So these are all implicitly defined because I can't get the one y all by itself. Here's the steps we go through. First, we're going to take the derivative with respect to x, like it says, of both sides of the equation. We want the derivative with respect to x of y, so if y is in here, then we need to take the derivative with respect to x of this, but that means also this, and the other side of the equation. So as we're jotting down our 4 steps, first, differentiate on both sides. Usually with respect to x, but it's with respect to whatever. So I say d dx, both sides. That's step 1. We wrote that we're going to differentiate. Let's actually do that. The derivative of the y cubed, 3y squared, but it's not a variable that matches the x, so we have to use the chain rule. Times the derivative of the inner function, the y, is dy dx. Same thing with this guy. 2y, that's only the derivative of the outer function. Y is the inner function, different than x, so times dy dx. Now this is a matching one, so if the letters match, I don't have to multiply by dx. Now if you really want to, say times dx dx. But what do you know that simplifies into? 1, so I'm usually not going to write that. Differentiating on the other side, the derivative of the constant is 0. The derivative of 5y is 5, but that's a different variable, doesn't match, so chain rule says times dy dx. So let's add to our notes that we're differentiating on both sides using the chain rule when the letters don't match. Okay, so we have our chain rule. We've done the derivative. Next, remember our goal. Let's keep the eye on the prize. We're trying to find dy dx. So how do I solve an equation when I have dy dx here, dy dx here, dy dx here? We have to collect all the dy dx's on one side. So that's what we're going to do next. Step 2, collect dy dx on one side of the equation. So here's step 2. I already have this one, and this one, and this one I need to bring over. This one's not a dy dx, so let's send it to the other side. 3y squared dy dx plus 2y dy dx minus, because I have to subtract this to the other side, 5 dy dx. This was not a dy dx, this 2x, so I'm going to add it to the other side, send this guy over there, 2x. 0, I don't need to write. So I've collected all my dy dx's. Now, we want, ultimately, eye on the prize, get dy dx by itself. So I have the dy dx's together. I can't combine them because they're not like terms, but I can factor out that common dy dx. Let's see what that looks like. Dy dx, 3y squared plus 2y minus 5. So step 3, factor out the common dy dx, because eye on the prize, that's where we're trying to go. What is dy dx? What does it equal? Finally, solving for dy dx. Last step, eye on the prize, dy dx equals, dy dx is multiplied to all of this, so divide it to move it over to the other side. 2x divided by 3y squared plus 2y minus 5. Step 4, solve for dy dx. And that's implicit differentiation. Why don't you give number 2 a shot? Pause video, come back, see if you're correct. First, derivative with respect to x of 2y, derivative with respect to x of x squared plus sine of y. Take the derivative of this side, 2, but the letters don't match, so chain rule, dy dx. Take the derivative of this side. The derivative of x squared is 2x. Letters match. Done with that one. Derivative of sine is cosine. But, letter doesn't match. Use our chain rule. Say times dy dx. Now we collect our dy dx terms. All on one side. Probably it's easier to bring those over there. 2 dy dx minus cosine y dy dx equals 2x. Then I've got a dy dx in common, factor it out. 2 minus cosine of y equals 2x. And finally, eye on the prize, dy dx, get it by itself, divide by what it's multiplied by. We're always going to be factoring out dy dx, or combining like terms to get a dy dx multiplied to something, always. So if you want to, in your steps, solving for dy dx always means dividing by the other stuff next to the dy dx. That's always going to be that last step. You want to look at a couple others? This one, be very careful, because as we get to this middle term right here, this is a product of different variables. Call it f is x cubed function, the g is y to the 5th function. So multiplied is product. We need a product rule when we get here. So when I take the derivative of y to the 4th, 4y cubed dy dx using our chain rule. In this part, the product rule, first times the derivative of the second. Y to the 5th becomes 5y to the 4th, but it's a y, so I say times dy dx. Plus second, y to the 5th times the derivative of the first, 3x squared. That's that product rule section. Minus the derivative of 2x to the 7th, 14x to the 6th. The derivative of 13 is 0, derivative of the constant. Now I want to get all my dy dx terms together. My non-dy dx terms, other side, other side. So let's write 4y cubed dy dx plus, probably rearrange these, put the number first, write it alphabetically. It looks a little bit better that way. Sending this guy over, setting this guy over, makes 14x to the 6th minus 3x squared y to the 5th, because I arranged that alphabetically, and it's a little bit prettier. Then, you've got it. Factor out the dy dx. dy dx, factored out, 4y cubed plus 5x cubed y to the 4th equals all this other side. And lastly, solving for dy dx, dividing by all of that, 14x to the 6th minus 3x squared y to the 5th over 4y cubed plus 5x cubed y to the 4th. Taking another careful look as we are doing the derivative, this is implicitly defined because y is here, y is here. I cannot possibly solve for y by itself. So I'm taking the derivative of this side, dy dx, with respect to x. Taking the derivative of x is 1. This one, it's tangent of more than just x. So this is a composite. So I have to do the chain rule here. First, the derivative of the outer function, secant squared. Don't touch the inner function. Then, the derivative of the inside function, xy, x times y. The derivative of that is using a product rule. Taking the derivative of that product, first times the derivative, dy dx, of the second, plus the second times the derivative of the first. I don't have to write that one, but I didn't want you to think I forgot about it. Now we need to get dy dx terms all by themselves. So dy dx here, dy dx here. I would probably find this easiest by maybe distributing the secant squared x, maybe subtracting the 1 first, dividing by the secant squared. No, let's do the distributing. Dy dx, 1 plus secant squared of xy times x dy dx plus secant squared of xy times y. Then collect my dy dx terms all on one side. We'll move that guy over. Dy dx minus secant squared xy times x dy dx. We're left on the right with 1 plus secant squared of xy times y. Factor out our common dy dx. 1 minus secant squared xy times x. And the other side, I'm tired of writing these parentheses, so I'm going to write the y in the front. Y secant squared of xy. Similarly here, I'm tired of writing the parentheses, so I'm going to write the x in the front. Finally, divide by what's multiplied to dy dx. 1 plus y secant squared xy over 1 minus x secant squared xy. Let's take a look at some more. Equation of the line tangent to this curve at this point. Equation of a line tangent. What do we need? Point and slope. Well, I gave you the point. Done. We need the slope. What slope? Change in y over change in x. Derivative if it's a line tangent. So I need the derivative of this. I cannot get y by itself, so I have to take the derivative implicitly. So starting with the x squared, 2x. This is a product. So let's do the product rule for that stuff. First, derivative of the second, x dy dx, plus second times the derivative of the first, 1. Then the derivative of y squared, 2y times dy dx, since the letters don't match, equals 0. Derivative of 7 is 0. Now be careful here because we're subtracting both of these. So perhaps you distribute before you try to collect terms. 2x minus x dy dx minus y plus 2y dy dx equals 0. Now we can do what we did before and collect the dy dx terms together, solve for dy dx, but let's keep our eye on the prize. Find an equation of the line tangent. We need the slope. We need the slope at the values given in the point, at that point. So perhaps it's a little bit easier to work with this if it were mostly numbers than mostly letters. Let's take our point x and y and plug it in here, maybe at this point. That might make it a little bit easier to work with. So instead of x, we'll put -1. Instead of y, we'll put 2. And now let's simplify. 2 times -1, -2. Plus, because minus a negative, dy dx, minus 2 plus 4 dy dx equals 0. Now we can combine the like terms. 1 plus 4 dy dx's makes 5 dy dx's. -2 and -2 is -4, and add them to the other side equals 4. Solve for dy dx, get 4/5. There's the slope of our tangent line. We need the equation of the tangent line. So finally, to write our equation, y minus the y-coordinate equals the slope times x minus the x-coordinate. Minus a negative makes plus. Done. Part B, find an equation of the line normal to the curve. If you don't know, normal means perpendicular. And perpendicular means the slope is the opposite reciprocal. Well, notice it's the same curve, it's the same point, same curve, same point. The slope we got before was 4/5. Opposite reciprocal to that, -5/4. So same point, new slope, slightly different equation. Y minus the y-coordinate 2 equals -5/4 times x minus a negative or plus 1. Let's try the equation of a circle. Find the second derivative for x squared plus y squared equals 1. Now, don't fool yourself. You can solve for y, but if you do, plus or minus the square root of 1 minus x squared. That means you have to do 2 equations, the derivative of 2 equations. That will not work for what we need. Let's just do the derivative implicitly. It'll be easier. First derivative before we get to second derivative. So first derivative comes before we can get to second derivative, means take the derivative with respect to x of each term. Solve for dy dx. 2y dy dx equals -2x. Divide by the 2y, the 2's will cancel out, we get -x over y. Now, here comes the fun part. Second derivative, which is what was asked for, means take the derivative with respect to x of what we already got, of dy dx on one side of the equation, the derivative with respect to x of -x over y from the other side of the equation, taking the derivative of both sides the second time. This side is our d squared y dx squared. See, d squared, dx, dx, dx squared. Over here, we have a quotient, so we should use the quotient rule. Bottom times derivative of the top minus top. Derivative of the bottom is dy dx over denominator bottom squared. We can simplify this a little bit, but here's what you have to remember in these. We have dy dx in our second derivative, but we know from here what dy dx equals. So take out dy dx, put -x over y in its place, and you will be able to simplify that much more. Now we don't have d's, we just have x's and y's. Negative y minus a negative negative makes minus x squared over y all over y squared. Now there's a variety of ways to simplify this so that it's not a complex fraction. One is, if I want to get rid of a denominator anywhere, I multiply by that number or variable. But if I do it to the top of a fraction, I have to do it to the bottom also. Let's see where that takes us. Negative, distribute the y squared. Y over y cancels that one out. Bottom is y cubed. Now here's where the magic happens. You ready? Don't blink. Factoring out the negative from the top leaves us with y squared plus x squared. Denominator is still y cubed. What is y squared plus x squared? Look back. Look closely. It's 1. So all of that can come out and 1 can go in its place, and we end with the most simplified version right here. And do you have to get there? Yes, you do. These will be multiple choice, and you have to know how to recognize that as your final answer. Why don't we try it again? But this time, we want to use the circle equation to find the second derivative at a point. So let's practice and plug it in. Maybe you pause the video and come back, see how you do. First derivative first. 2x plus 2y dy dx equals 0. Derivative, derivative, chain rule, 0. Solve for dy dx. 2y dy dx equals negative 2x. Divide. Negative 2 divided by 2, negative 1, so there. Notice how we ended up with the same thing. Circle equation, constant doesn't matter, its derivative is 0. You'll get used to it as you go. Now, second derivative. Derivative of this side is d squared y dx squared. Quotient rule here. Denominator, derivative of numerator, minus numerator, derivative of the denominator, dy dx over denominator squared. Simplify, and as you simplify, remember we know what dy dx equals, so substitute. Negative y minus a negative negative is minus x squared over y, all divided by y squared. Perhaps you practice simplifying it algebraically, or maybe at this point, you plug in that point. At this time, you plug in that point. But I want you to practice simplifying algebraically, so let's watch that magic happen. Multiply to the top and bottom by y. Distribute that, and we get negative y squared minus x squared over y cubed. Factor out the negative, y squared plus x squared over y cubed. You recognize what x squared plus y squared equaled from the beginning. So you wrote negative 25 over y cubed. Then we have less to plug in, less number crunching. Y is 3. So at the point 4, 3, we get negative 25 over 3 cubed, or negative 24 over, oh, where'd my 24 come from? Let's fix that. Negative 25 over 3 cubed, or negative 25 over 27. Let's look at a couple other examples that deal with needing to do implicit differentiation. Find the points where, if any, there may not be any, where g of x has any vertical tangent lines. Think about what that means. A vertical tangent. The slope is undefined. The slope is undefined. Well, what is slope? Derivative. So g prime has to be undefined. Where is g prime undefined? Well, we need g prime first. So we find the derivative, and I don't see any y's over here, so it looks like I don't need implicit differentiation. 0 minus, treat that as x to the 1/3, and we have 1/3 x to the negative 2/3, or negative 1 over negative 3x to the 2/3. Now, g prime is undefined. Where is this undefined? Always when there's a denominator, it's where the denominator equals 0. So let's solve for where the denominator is 0. Divide by 3, exponent whatever, x equals 0. That is where g of x has vertical tangent lines. But notice it says find the point. Find the point. That's only the x coordinate. Point is the x and the y. Where do you find the y once you know the x? The original function. What is g of 0? 3 minus the cubed root of 0, which is 3. 0, 3 is our point. Now really, I was just warming you up for this one. This was from an AP exam where it says, consider this curve. Find the x-coordinate, so we don't need the whole point, just the x-coordinate of each point, perhaps there's more than one, on the curve where the tangent line is vertical. So again, think to yourself, that's where the derivative is undefined. So we need a derivative. If I have x's and y's, that means I need dy dx. Product right here. So product rule. First times the derivative of the second, 2y dy dx plus second times the derivative of the first. There's the product rule for that part. Next one is another product. So minus, and then let's do that other product. First times the derivative of y is dy dx plus y times the derivative of the second, 3x squared. I put the brackets because of the minus. I don't want to mess up my signs. Equals 0 on the other side. Now we need dy dx. So let's find all the dy dx's and get them by themselves. dy dx, send the rest over. So alphabetizing 2xy dy dx. This can go to the other side. So over here equals negative y squared. This stays, it's a negative. Negative x cubed dy dx. This can go to the other side. Keep notice that it's a negative of that. So when I send it to the other side, it's a positive 3x squared y. Alphabetize. Now we can factor. Dy dx factored out. 2xy minus x cubed left over equals negative y squared plus 3x squared y on the other side. And divide. Dy dx is negative y squared plus 3x squared y over 2xy minus x cubed. Keep your eye on the prize. Where are we going? Where is the derivative undefined? Is the translation of where is the tangent line vertical? The derivative is this. The derivative has a denominator. Where the denominator equals 0 is where the derivative will be undefined. Problem. We have one equation now. 2xy minus x cubed equals 0. But two unknowns. We need two equations if we're going to solve two unknowns. Where's our other equation? There's our other equation. So let's take our two equations. Xy squared minus x cubed y equals 6 from the top. And 2xy minus x cubed equals 0 from the bottom. Let's do a substitution to figure out the x coordinate that they ask for. I see this one looks like there's a little bit less in there, so perhaps I solve for one of the variables in that one. Let's take this and get the x cubed over there, add it, then divide by 2x. So y equals x squared over 2. Take what y equals from this equation and plug it in to that equation everywhere we see y. So now here's what it looks like. X times instead of y squared, x squared over 2 squared minus x cubed instead of y, x squared over 2 and equals 6. Now we have an equation where everything's in terms of x. Let's be careful as we simplify. X times this. We'll have to square this first, so that'll become x to the 4th times x is x to the 5th Oops, not over 2, because I have to square the denominator as well. 2 squared makes 4. Or we can think of that as 1/4 x to the 5th. Here, add the exponents, x to the 5th with 1/2. Notice I have like terms. I have a 1/4 x to the 5th minus a 1/2 x to the 5th. How about we think of that as 2/4? That translates down to negative 1/4 x to the 5th. Multiplying by negative 4 makes x to the 5th equal negative 24. And taking the 5th root leaves us with just the 5th root of negative 24. Let me write that a little bit better. X equals the 5th root of negative 24. So happy that we got that AP problem, as you will be when you're taking the AP exam.